Okay, in this session we're going to discuss about the power triangle. In the previous video there's a mistake about the phase shift between the inductive voltage and the inductive current. Now I'm making new video which is the corrected form. Okay, let's write here. We're going to discuss about the power triangle. Now power triangle, it is the representation of geometrical representation of the apparent power, which is given by S, and then the unit for this one is the volt ampere, or is simply the multiplication of the voltage and the current. And second one, it is the reactive power, which is represented by the Q, and then the unit is given by volt ampere reactive. And then the third one is called the true power, or we also call it the real power, or we also call it a active power, and then it's represented by the P, and then unit is watt. So the power triangle is the geometrical representation of the apparent power, reactive power, and then the true or real or active power. Now if you draw the Phasor relationship for the voltage and current for all kind of load. Now we have usually we talk about the three loads. First one is resistive load. Now in case of the resistive load, your voltage and the current are in phase, which means you will only have the true power is given by VI. So with this, and then your unit will be in the watt. Now in case of the purely resistive load, your apparent power will be 0, the true power will be VI, and then reactive power will be 0. And then in the second one, if for the inductive load, okay, for the inductive load, we know that the phase shift is between 0 to 90 degree. Now if you draw the Phasor diagram for the inductive load, we have the voltage, and then we have the current I. Now this voltage is leading the current by phi, or that current is lagging the voltage with the negative phi. Okay, let's write here negative, which means voltage is leading the current or current is lagging the voltage. And then if you draw the Phasor diagram for the current for both apparent power, reactive power, and then for the true power, you'll have the current triangle here. Now here we will have current, yeah, I cos phi, and then here we will have I sin phi, and then here we will have I. And then if you multiply, okay, let's write this Phasor diagram A, Phasor diagram B. If you multiply the Phasor diagram B with the voltage, then we will have another Phasor diagram VI cos phi, and then here we will have VI sin phi, and then here we will have V and I, and here we will have phi here. So which means this one is called the true power, and here is the reactive power, and this one is called the apparent power. So with this you can write that your S is equal to VI, and then your Q, the reactive power, is given by VI sin phi, and then your true power is given by VI cos phi. Now this is the power triangle representation for the inductive load. Now this is the only difference that we have for the inductive load. The main difference between the inductive load and the capacitive load on the power triangle is here the current is lagging behind the voltage, or voltage is leading the current. And then for the purely for the capacitive load, let's say capacitive load, your phi will be between again 0 to 90 degree, and then in this case you'll have the voltage, and here you'll have the current. current phi, and then here it is leading, current is leading the voltage. Now similarly, if you do the current angle for this one, for both reactive, apparent and the true current here, it will be I cos phi, I sin phi, and then here you will have V. Okay, here you will have I, and then again similarly, if you multiply it with the voltage, then you will have okay, I'm going to write it here directly. Okay, Vi cos phi, here you have Vi sin phi, and then here it will Vi, and then this one is called the apparent power. Here again you have reactive power, and then this one is true power. The same thing, only thing is now we have to understand whether the current is leading or lagging in terms of the different type of load. For the inductive load, your voltage is leading the current, and then for the capacitive load, your voltage is lagging the current, or current is leading the voltage. So it's just like the representation, the direction of the Phasor diagram. The power angle will give you the relationship between the geometrical relationship between apparent power, reactive power, and then the true or the real power. So from that power angle, you will be able to derive the S, the apparent power, which is given by root of P square plus Q square. And then similarly, if you're trying to find the phi, okay, now in the true power, you will know what's meant by cos pi. This is called the apparent power. This is called the power factor. Now this one will is the ratio between the true power and then the reactive power. So now okay, if you write the cos phi, it will be 2 power p to the apparent power. It's not with the reactive power, it's the ratio between the true power and the apparent power, which means your phi will be given by cos inverse of p by s. Now this is how we should be finding the phi, if that real power and then the apparent power are known. Or you can also find the phi using sine inverse of reactive power divided by s, or you can also use by tan inverse of that I think is p by q. So this is the application of the power angle. With the power angle, we will be able to find the apparent power here, see, using this Pythagoras theorem. And then again, using the trigonometric ratios, we can also find the power factor and then the phase angle between the voltage and the current. So that's it.